Section 2.5, zeros of polynomial functions. In this section, we will use the rational zero theorem to find possible rational zeros. We will find zeros of polynomial functions. We will solve polynomial equations. We will use the linear factorization theorem to find polynomials with given zeros, and then briefly discuss Descartes' rule of signs. The rational zero theorem. We will use the rational zero theorem to find all possible rational zeros. So the rational zero theorem states that if f of x is given by the polynomial a sub n x sub n plus a sub n minus 1 times x sub n minus 1 plus a sub 1 times x plus a sub 0, and the quotient p divided by q is a rational zero of f. All right, so if that is the case, then we want to say then that p is a factor of the constant terms a sub 0. Here's our constant term. All right, so what we're basically saying here is that, and q would be a factor of the leading coefficient a sub n. So let me just briefly reiterate that the possible rational zeros, all right, would be p over q. So factors of the constant term divided by factors of the leading coefficient. Now let's look at an example where we have to list all of the possible rational zeros of the function f of x is equal to x cubed plus 2x squared minus 5x minus 6. So we're going to use the rational zero theorem. Remember, we said that we're interested in p divided by q, where p represent the factors of the constant term, and in this case the constant term is a -6. And q again represents the factors of the leading coefficient, and in this case it's 1. All right, so let's see what we have here. So p divided by q would be all of the factors of a -6. So we have plus a -1, plus a -2, plus a -3, plus a -6, divided by factors of the leading coefficient. The leading coefficient is 1, so of course it's plus or minus 1. So So plus 1, plus or minus 2, plus or minus 3, plus or minus 6 upon dividing by plus or minus 1. So these are the possible rational zeros. Let's consider another example. Let's list all of the possible rational zeros of f of x is equal to 4x to the 5th plus 12x to the 4th minus x minus 3. All right? So let's see. The constant term is a negative 3. The leading coefficient is 4. All right, so all of the possible rational zeros, all right, can be found by looking at, remember we want factors of the constant term negative 3 divided by factors of the leading coefficient four. So the factors of the constant term, a negative 3, would be plus or minus 1, plus or minus 3, divided by factors of the leading coefficient 4. So let's consider the factors of 4. They are plus or minus 1, plus or minus 2, and plus or minus 4. So as we now record the leading coefficients, so we're going to do this division, so that will be, we're going to divide 1 by each of the terms in the denominator as well as 3. So what do we have here? Plus or minus 1, plus or minus 3, plus or minus 1, plus or minus 1 divided by 2 would be plus or minus 1/2. Plus or minus 1 divided by plus or minus 4, we have plus or minus 1/4. Plus or minus 3 divided by 1 is going to be plus or minus 3. We already have that. Plus or minus 1, plus or minus 3 divided by 2 is going to be plus or minus 3 over 2. And then finally 3 plus or minus 3 divided by plus or minus 4 will give us plus or minus 3/4. So these represent all of the possible rational zeros. In the next example, we actually want to find the zeros of a polynomial function. In the previous example, we listed all of the possible rational zeros. But this time we're going to actually find them. All right, but let's begin by listing all of the possible rational zeros. All right, so the possible rational zeros are, all right, we want factors of the constant term, so the factors of a negative 20, so let me just write this, factors of a negative 20 divided by factors of the leading coefficient. The leading coefficient is 1, so we want factors of 1. So the possible rational zeros then can be listed as, so all of the factors of a negative 20, so we have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. All right, factors of 1, of course, 1. All right, so these are the possible rational zeros. All right, now we have to make a determination. Which are the zeros? In order to make this determination, we will use synthetic division. We're going to use synthetic division to see if we can find a rational zero among the possible rational zeros. Keep in mind that if f of x is divided by x minus c, and the remainder is 0, then we concluded that c is a zero of the polynomial. All right, so let's begin. All right, let's begin by testing 1. All right, so I'm going to use synthetic division. All right, so our divisor is, in this case, 1. X minus c. C is 1. All right. So in synthetic division, we're going to now record the coefficients of each of the terms. So we have 1, 8, 11, and a negative 20. On the bottom row, we bring down the leading coefficient 1, and we begin the multiplication. 1 times 1 is 1, and then we add. 1 plus 8 is 9. 1 times 9 is 9. 9 plus 11 is 20. 1 times 20 is 20. And now when we add, a positive 20 plus a negative 20 is 0. So the quotient is given by the bottom line. So the quotient upon dividing by x minus 1 would be x squared plus 9x plus 20 is equal to 0. Now the next step, if we can now solve this quadratic equation by factoring. So if we factor, we have x plus 4 times x plus 5. Using the zero product principle, we have x is equal to negative 4 and x is equal to a negative 5. So therefore, the zeros are negative 5, negative 4, and 1. Another example. Let's solve the equation x to the 4th minus 6x cubed plus 22x squared minus 30x plus 13 is equal to 0. To solve this equation, when you solve an equation, we characterize the solution as the solutions or the roots of this equation. So the possible rational roots can be found in the same manner as we found the rational zeros. So we want to consider the factors of the constant term 13 divided by the factors of the leading coefficient, which is 1 in this case. So the factors of 13 are plus or minus 1, plus or minus 13, all divided by factors of 1, of course, plus or minus 1. So plus or minus 1 and plus or minus 13 are the possible rational zeros. All right? Okay, let's begin. All right, we're going to start with 1. We'll start with 1. All right, so we're going to use synthetic division to make a determination regarding the zeros of, or the roots of this equation. So if I begin with 1, using synthetic division, now let me record the coefficients of each term. So I have 1, negative 6, positive 22, minus 30, plus 13. All right. The leading coefficient 1 is on the bottom row. So 1 times 1. We're going to now begin the process. We begin by multiplying 1 by 1, which is 1. And now we add. A positive 1 plus a negative 6 is a negative 5. 1 times a negative 5 is a negative 5. And now you want to add. A negative 5 plus 22 is a positive 17. 1 times 17 is 17. 17 plus a negative 30 is a negative 13. 1 times a negative 13 is a negative 13. Upon adding, we get 0. So what do we conclude? We conclude that, therefore, 1 is a 0. And now the quotient, upon dividing by x minus 1, the quotient is 1, negative 5, 17. All right, so in other words, we have 1 x cubed negative 5x squared plus 17x minus 13. Now the reason I've written just the coefficients again, let's see if we can use the possible rational tests to determine if 1 is also a 0 of this new polynomial. So let's try dividing by 1 again. All right? If it doesn't work, we go on to perhaps try a negative 1. That doesn't work, we try 13 or a negative 13. But let's try 1 on the resulting quotient here. So we have, bring down the leading coefficient 1. So 1 times 1 is 1. A plus 1 minus 4 is a negative 4. 1 times a negative 4 is a negative 4. A negative 4 plus 17 is 13. 1 times 13 is 13. So what do we conclude? We conclude that 1 is actually a double root. So 1 is a double root. All right? So what we have now, let's record what we have now. We have, so now the quotient, upon dividing a second time by x minus 1, the quotient is x squared minus 4x plus 13 is equal to 0. So now we want to solve this quadratic equation. It doesn't factor. So what we need to do is to use the quadratic formula. So continuing, x squared minus 4x plus 13 is equal to 0. Remember, we said that it doesn't factor. So in order to solve this quadratic equation, we are going to use the quadratic formula. All right? So upon using the quadratic formula, we have x is equal to minus b. B in this case, as you can see, is a negative 4, but minus b is minus a minus b. So minus a minus 4 plus or minus the square root of b squared minus 4 squared minus 4 times a is 1, times c. C is 13, so 4 times 1 times 13. Divided by 2 times a. A is 1. 2 times 1 is 2. So let's simplify. So we have a negative times a negative 4, so positive 4 plus or minus, simplifying the expression under the radical, we get a negative 4 squared is 16 minus 4 times 13 is a negative 52. Excuse me, it's, yeah, a negative 52. all divided by 2. Continuing to simplify, 4 plus or minus the square root of 16 minus 52 is a negative 36 divided by 2. So if we simplify here, we have 4 plus or minus the square root of a negative 36 is 6i, all divided by 2. Simplifying, we have 2 plus or minus 3i. So the solution set is 1 from our first computation, 1, and we have 2 plus or minus 3i, which would be 2 plus 3i and 2 minus 3i. The next theorem that we want to introduce you to is the linear factorization theorem. The linear factorization theorem states that if f of x is given by this polynomial, a sub n times x sub n plus a sub n minus 1 times x sub n minus 1 plus so on, plus a sub 1 times x plus h of 0, where n is greater than or equal to 1, and the leading coefficient a sub n is not equal to 0. So if that is the case, then we can conclude that we can express f of x as the product of its linear factors, where c sub 1, c sub 2, all the way out, c sub n are complex numbers. So, the linear factorization theorem tells us that an nth degree polynomial can be expressed as the product of a non-zero constant, a sub n, and n linear factors, where each linear factor has a leading coefficient of 1. Let's now look at an example of how to use the linear factorization theorem. You may recall from your reading that if a plus bi is a root of a polynomial equation, then a minus bi is also a root. In other words, imaginary roots occur in conjugate pairs. The given zeros in our problem are a negative 3 and I. Now, because I is a 0, from the property, we also know that minus I must also be a 0. So now let's use the linear factorization theorem to answer the question, to find a third-degree polynomial function with real coefficients with these properties. All right, so by the linear factorization theorem, we have that f of x is equal to a sub n times x minus c1 times x minus c2 times x minus c3. Therefore, we have a sub n is equal to x minus c1. So the first 0 is a -3. So that's x minus a -3 times x minus c sub 2. Well, the next 0 is I. So we have x minus I as a factor times x minus c sub 3. The other 0 is a -I. So we have x minus a minus I. Simplifying a bit, we have a sub n. X minus a minus 3 is going to be x plus 3. And let's do this multiplication over here. If we do this multiplication, we're going to get what? We're going to get x squared minus I squared, which is x squared minus a minus 1, which is x squared plus 1. So upon multiplying x minus I times x minus a -I, we're going to get x squared plus 1. So we have f of x is equal to a sub n times x plus 3 times x squared plus 1. Okay, let's go back to the statement of the problem. We're also given that f of 1 is equal to 8. So if I evaluate the function the function at 1, we have f of 1 is a sub n times 1 plus 3 times 1 squared plus 1. Simplifying, we have 1 plus 3 is 4. 4 times 1 plus 1 is 2. 4 times 2 is 8. So we get 8a sub n. But we know that f of 1 is equal to 8. This is f of 1, so I can conclude that 8a sub n is equal to 8. All right. Now, we can now solve the equation 8 times 8 sub n is equal to 8. So, dividing by 8, we get a sub n is 1. So, therefore, f of x can be expressed as x plus 3 times x squared plus 1. We're going to multiply this out. You get x cubed plus 3x squared plus x plus 3. So we have found a third-degree polynomial function with real coefficients that has a -3 and I as zeros. In the next example, we want to determine the possible number of positive and negative real zeros of f of x is equal to x to the fourth minus 14x cubed plus 71x squared minus 154x plus 20. So we're just going to determine the possible number. We're not going to find them. We just want to determine how many are there. And we will be using Descartes' rule of signs. All right? The rule is based on considering variations in signs between consecutive coefficients. So let's see what we have here. So f of x is x to the fourth minus 14x cubed plus 71x squared minus 154x plus 120. All right, so we're going to look at this, the change in sign. So from x to the fourth to a negative 4x cubed, we have a sign change. So here's a sign change. It goes from positive to negative. From a negative 14x cubed to a positive 71x squared, there's another sign change. I'm just going to note that, sign change. Another sign change. And another sign change. So we have a total of 4 changes. So according to Descartes' rule of signs, the number of positive real zeros of the function is either the same number as the number of sign changes. So there are 4 sign changes. So first of all, there are 4 positive real zeros, or the number of positive real zeros will be less than the number of sign changes of the function f of x by a positive even integer. So what does that mean? All right, so we have a total of 4 changes. All right, so there are either 4 possible real zeros or 4 minus 2, because we said the number of changes less than the number of sign changes by a positive integer, positive even integer. So this would be 2. So we began with 4, so I want to reduce it by the positive even integer 2. And I can go one more step, 2 minus, and then 2, again reducing it by a positive even integer 2, I get 0. So therefore, by Descartes' rule of signs, the function f of x has 4 changes of signs, and they are 4, 2, or 0 would be all of the positive real zeros. All right? Also, according to the rule, to determine the number of negative real zeros, we would have to compute f of minus x. But since f of minus x has no changes of signs, there are no negative real zeros.